Hey, it's Michael. I'm going to try to walk you through a Verilog implementation of a numerically controlled oscillator. This is a special one because this simultaneously generates quadrature sinusoids, a sine and a cosine output. So if we go online, there's all kinds of information that explains exactly what a numerically controlled oscillator is. And I'll jump into this one, for example. Thanks, Don Hummels. The core of a numerically controlled oscillator is something called a phase accumulator. It's just an adder. In the implementation I will show you, we use a 32-bit adder, and we take the upper 12 bits of that adder and we drive what's shown in this block diagram as a phase to amplitude converter. Well, what is that? A little further down, it's another block diagram. It's a lookup table. And a lookup table is just a series of, it's like a ROM or a RAM. You provide an index to it, it outputs data. In our implementation, our lookup table is going to drive 12-bit data, and that data will give us both sine and cosine simultaneously. So what does that look like? Well, here's our Verilog um, Quadrature sinusoid generator, as I call it. And it's got a clock and a reset and an enable. Let's just imagine that enable's always one. And what we have in as an input is a phase increment. And this is the 32-bit value that is going to be continuously added to the phase accumulator. We're just going to allow that adder to continually add and overflow and use the upper 12 bits to drive the phase output that will ultimately drive our lookup tables. So here's the implementation for the phase accumulator. There's not much to it. Reset everything to 0, and then as long as you're enabled, you continuously add phase increment to the phase accumulator. And then we take the upper 12 bits of the phase accumulator and drive it out as phase. So the magic to this implementation is in the lookup table or lookup tables. What we are going to do is we're going to create lookup tables that contain the first 45 degrees of a sine in one table and the first 45 degrees of a cosine in the other table. And we are going to combine these to create the full cycle of both a sine and a cosine. There's a little bit of magic to creating that table, so I'll pop into Excel and show you what that magic looks like. I'll try to get zoomed in here. See if I can move this over here. The magic is in our lookup table, we start with an offset of 0.5. And what that does is it allows these two lookup tables to be used without overlapping. Neither of them contain the data for uh, phase 0 degrees or phase 90 degrees. The data contained is offset by half an increment. So in this implementation, we have 45 degrees of a sine, 45 degrees of a cosine. So how do we use them? What we do is we piece the sinusoid, and we'll go through the cosine later, together from the two tables. So when we start at phase 0, we increment through the sine lookup table until we get to 45 degrees. And then we go backwards through the cosine table from 45 degrees back to 0. And then forwards through the cosine table from 0 to 45. And then backwards through the cosine table from 45 to 0. Okay? That brings us through the positive side of the sinusoid. And then we do the same thing again, forward, backward, but now we invert the output of the table. So where the table's giving us positive values here, we just take those values and invert them, and that completes the rest of the sinusoid. In our implementation, that 12-bit phase output, the upper 12 bits of our phase accumulator, is used such that the upper 3 bits encode the octant, one of 8 octants, and the lower 9 bits form an index into the lookup tables. So here we have the lookup table index, and we are alternately inverting it based on bit 9 of the phase. And that lookup table index feeds into our sine lookup table and our cosine lookup table. Each of these lookup tables contains, in our implementation, 512 data values for indexes 0 to 511. So this 9-bit lookup table index, or LUT index, will increment from 0 to 511, and then decrement from 511 back to 0, increment from 0 to 511, and so on, as we go through all 8 octants, as we go through the full 0 to 360 degrees of the sinusoid. Now, as we go from one octant to another, the sine data is alternately coming out of the sine lookup table and then coming out of the cosine lookup table, and so forth. It ping-pongs back and forth. Meanwhile, the cosine data is doing just the opposite. We start by pulling data out of the cosine lookup table, then from the sine, and so forth. And that's how we piece together the cosine. Hey, so let's have a look at these lookup tables. So we have the 2 lookup tables containing 45 degrees of a sinusoid, 45 degrees of a cosine, from 0 to 45 degrees. The lookup table in Verilog, and in VHDL for that matter, is just a big case statement. So your input is your index or an address. Your output is your data. In this case, we have a lookup table containing 512 data points. So we need a 9-bit address. So there I have a case statement on my index. There'll be 512 of these from 0 to 511. And then I've taken the data generated by that Excel spreadsheet. You can see the values there, 2, 5, 8, 11 for the sine. Pop back to there. So all I've done is use some column copy and paste into a text file using Notepad++, my favorite. So, and I've created my big case statement here. So there's my sine lookup table from 0 to 511, values from 2 to 1446, my cosine lookup table. So the cosine's going to, that's at 0, it's going to be at the maximum value, in this case 2047, and then that's going to slowly ramp down to whatever it is at 45 degrees here. Looks like 449, 14,449. So just a few ticks off the highest value in the cosine lookup table. So big case statement, pretty easy to implement. One thing I want to touch upon is how do we generate these values? I've shown you the spreadsheet, but I haven't shown you the math. So for a 12-bit value, I want my values to be symmetric about 0. So for a sine 12-bit value, essentially it goes 0 to 247, 0 to minus 2048, but I'm not going to go all the way. I'm going to keep it symmetrical. So it'll go from positive 247 to negative 247 as I go through. Since I'm only storing the first 45 degrees, all my numbers are going to be positive, and therefore I don't need 12 bits to store the data. I only need 11 bits, which is why you see these values are just 11-bit values. We'll take care of creating the full sine 12-bit value in the math at the above the level of the lookup table. All right. And the next thing is, how do we calculate that magic phase increment value? Well, there's the fundamental equation. The output frequency is equal to the sample rate. That's the frequency of that clock signal that we're clocking everything at. This guy right here. I often use 100 megahertz. We could clock it higher depending on the logic you're implementing this in. But if we are clocking, if our F sub S, our sample rate is 100 megahertz, we have a resolution of 23.3 millihertz. All right, so one tick, if our phase increment is 1, we'll get 23.3 millihertz. And everything else is an integer multiple of that. As a result, we can't get, say, 1 megahertz or 10 megahertz right on. There's always a little bit of frequency error. All right. The highest frequency, obviously, would be F sub S over 2, but that's not very useful because if you're hitting just the 0.0 and the midpoint of the sinusoid, it's always going to be 0. You're just going to be hitting the 0 point. So I don't typically try to run much above, say, 40% of S sub S and so forth. All right. So as an example, what if we wanted to generate 1 megahertz? We can rearrange this equation to put the phase increment there on the left side. The phase increment is equal to F out, which is 1 megahertz, times 2 to the power of 32. That's the full value of our phase accumulator or phase increment, divided by F sub S, which is basically 2 to the power of 32 divided by 100. And there you go. I expressed it in hex so you could see that it's a 32-bit value, or it fits within a 32-bit range. All right, so this might be a little bit much to take in, but there's a simulation of this Verilog code, this implementation of a quadrature sinusoid generator in Model Sim. And I'm just going to show you what's happening at the transitions. So at the start of time, our LUT table index is 0, and we are in octant 0. And so we are traversing through the sine lookup table from I don't know why it's doing that. Let me zoom in a little bit. We are traversing through the sine lookup table from 0 to 45 degrees. And then we make a transition from the sine lookup table to the cosine lookup table. So these, I don't know if you can see this in the resolution we're recording at, but here's the lookup table index. And we'll just zoom in here. And that's the highest index for 9-bit. So we've hit essentially 45 degrees or the end of the table. And now we are transitioning from octant 0 to octant 1. And we're changing the direction. So, we've incremented from 0 to 511. Now we're going from 511 back to 0. And we're also switching tables. So the last output from the sine lookup table was 1446. And the last output from the cosine lookup table was 1449. If I look at my sine data, here we have the value 1446. It's shifted over because this is a pipeline. We go from 1446 to 1449. So there's the transition from the data coming out of the sine lookup table to data coming out of the cosine lookup table. And the same thing is happening for the cosine data. Here's the last data in the cosine lookup table, and the first data, this is the data from 0.511 in the sine table. So we've made the transition from octant 0 to octant 1. I could go through the other transitions, but I'm sure you go blind looking at all this stuff. So I've put together a little simulation where I've gradually increased the phase increment from essentially an integer 1 to an integer 2. When I say integer, we are just changing the lowest order bit in the integer portion, the upper 12 bit of the phase accumulator. And by incrementing the phase increment or doubling the phase increment, we've doubled the output frequency because we're stepping through the lookup table twice as fast. And here we've tripled the output frequency. We've gone from a phase increment of 2 to a phase increment of 3. And now we're at 3 times the frequency and 4 times the frequency, and so forth. So this is a very useful tool to have in your toolbox. I use it to test stacks. I use it to make tones. It's once you've mastered this logic, you can modify it to support 8-bit DACs, 10-bit DACs, 16-bit DACs by changing the width of the data. I'm trying to get to the width of the data in the lookup table, or you can increase or decrease the actual size, the number of data points in the lookup table. If you want to save space, or if you have more space, you need more resolution. I've put this all in an Excel spreadsheet so I can easily modify the number of bits and the number of points in the full 360-degree phase of the sinusoid. So in this case, 4096 points. I only need 1/8 of that. That's 512. And so this table's 512 data points long. Fairly easy math. I can quickly point to that. Oh, not there. Sorry. But the sine data is merely a simple calculation where it's the index here, the value here, times 2 pi divided by 4096. And then we're going to scale that by the amplitude. In this case, it's half full scale. Full scale would be 4095, half of that 2047. And there you go. Hope that helps. Let me know in the comments if I can do better. All right. Take care.